Hello, in this lecture we're going to discuss classes, one of the key components of object-oriented programming. So, what is object-oriented programming? As programs get larger, it becomes increasingly difficult to maintain a large collection of loosely related functions. To overcome this problem, computer scientists invented object-oriented programming, a style in which tasks are solved by defining abstractions of real-world objects and having them collaborate to solve problems. Each object has its own set of data to set together with a set of functions that can act upon that data in a nice, clean package. These functions are called member functions, or methods. A class describes a set of objects with the same behavior. Objects are used to represent the domain of the problem, that is, the abstraction of the details of your problem. For example, if you're building a payroll system, you might have an object representing an employee. You might have an object representing a pay period or a paycheck. In C++, a programmer doesn't implement a single object. Instead, the programmer provides a class. A class is a template for a set of objects with the same behavior. Using an analogy as before, you can think of dog as a class, and your dog, Rufus, as an instance of that class, which has details identifying it as Rufus. The string class, for example, describes the behavior of all strings. The class specifies how a string stores its characters, which member functions can be used with strings, and how the member functions are each implemented. When you develop an object-oriented program, you create your own classes to describe what is important about an abstraction. Usually, you take the nouns out of your problem description, although that isn't enough. But those form the basis of some of your objects. Every class has a public interface. The public interface is a collection of member functions to manipulate the objects of a class. Private data members allow a programmer to hide the implementation of a class from a class user. Think about that in terms of a car engine. Okay, you use the interface to a car engine. You use the gas pedals, you use the steering wheel. You don't use any of the things directly behind it, and you don't know about them. You can replace your gas engine with an electric engine, and they drive the same way, with minor variances, but essentially you work with the abstraction, the steering wheel and the pedals, and the implementation is hidden behind the details. Similarly with a string, you don't need to know how a string organizes a character sequence or how C an object reads input from the console. All you need to know is the public interface, the specifications for the member functions. Basically, the public interface is the object's contract with the users. It says, I will provide you these services. The process of providing a public interface while hiding the implementation details is called encapsulation. Encapsulation and abstraction are two of the key features of object-oriented programming. There's two others we'll learn about later. Encapsulation is the act of providing a public interface and hiding implementation details. Use encapsulation for your own classes. When you define a class, you will specify the behavior of the public member functions, but you will hide the implementation details. Encapsulation benefits the programmers who use your class. They don't need to know anything about the implementation, and you can change it behind the scenes if you need to. When developing a program over a long period of time, implementation details often change. You try to use this data structure behind it or that data structure. Encapsulation is crucial to enabling these changes. When the implementation is hidden, the implementer can make improvements without affecting users of the class. C++ introduced the class to improve on the struct. Consider a dog. The term dog represents a class. That is the general abstraction for a dog. The dog class may have operations on it that apply to any dog. Bark, wag, run, etc. This is our dog class. Notice it's non-specific. This generic template may be thought of like a cookie cutter. The generic class doesn't tell us anything about our dog. To do that, we would need to gather some properties or attributes such as name, age, weight, etc. Consider my dog Charlie. Charlie isn't a class. This is Charlie. He's an instance or object of class dog. This means that he has properties specific to Charlie, but not to every dog. His name is Charlie. His breed is a pug. His disposition is absolutely evil. He's a fawn-colored pug, and so on. So he is an instance of the class dog. As an instance of class dog, you could apply the standard dog operation on him like bark, wag, run, etc. But you could also have separate details that apply to only him as additional functions. So how do we implement a class? To implement a class representing a dog, we start with the class definition. Here we say class dog, which is the class name, and we provide the fields just like in a struct, string name, breed, etc. If we do not make these explicitly public, they are private, meaning people outside the class implementation can't see it. So this is our private area, fields, attributes, and members, as they're called. Then we have a public area. We have dog, which is a constructor, which is the first thing that happens when you create a new instance. We have the method walk, which returns nothing. We have the method bark, which returns nothing. We have double get weight const, which means the result doesn't change anything internal to the object. Similarly, we have get breed, get name. Then we, which are also consts, we have set name, which sets the name. So to create a dog to represent Charlie, we could create an instance of object and set its properties are called methods on it. Dog Charlie, and we set its name to Charlie and say Charlie.bark. So now we implement the details of the dog class. We have void walk. Notice the double colons. It means this is an implementation. We have bark, which we use the member variable name of name. We have get name, which just returns the name, and set name. We don't want to access name directly. Okay, so let's take a step back, and now we're going to come over and we're going to actually implement our dog class here. So what we'll do, we always want to encourage reuse when possible. So what we're going to do is we're going to define our dog class in a header file. So we'll create a new header file called dog.h. All right, and in it, we're going to say first, pragma once. And we should appropriately comment it, but I'm not doing it for this demo. We'll say class dog. Okay, and open bracket, close bracket, and make sure to put a semicolon after that. And we're going to define our private members. And the members we're going to use are, we're going to define our private fields. Now, you can explicitly say private if you want to, but you don't have to. I actually like to do that, but we'll define our private fields: string name, string breed, string color, string disposition, double weight. Okay, now we're going to define, these are private members. The outside world can't see it except through our public interface. Now we're going to define our public interface. We've got our dog constructor, which is a special function that's called whenever you create a new instance of a dog. Okay, it's where you can initialize variables and that sort of thing. Then we'll have void walk. Then we'll have void bark. Then we'll have double get weight const, double get breed const, and, oops, that's a string. And then we'll have string get, and that can also be a const. And string get name, which can also be a const. These are called getters, and what they do is just get the value of a private field. And similarly, setters do the same thing, but they set the value. So here we'll have setters. Let's see, we'll have void set weight. It's going to take one parameter, which is a double. Okay. Then we'll have void set breed. We'll call string new breed. Okay. And obviously we're not setting these as constant because we're going to modify the object. And similarly, we'll have get disposition, which is void set disposition. And it'll take a string, and we'll have a set name. Alright, so this is our class definition. Now, we have to also implement our class. Now, there is something you can do to do this all in line, but we're not going to do that in this example because we want to show how to do it separately. So what we're going to do is we're going to create another file, dog.cpp, which has our implementation. Now, in here, we're going to include dog.h. Okay, you don't technically need to do this. Actually, let's not do it just in this example. Let's take the functions we have defined in dog.h, these guys, and we want to implement them. Now, when you implement them in a separate file, you got to let them know they're part of the class dog. And so the way we do that is we prefixed it with a scoping operator with the class name. Okay. And here, actually, let me fix this and include dog.h. Sorry about that. Alright, so here's the implementation of dog. We're not going to do much in our constructor. Let's just make sure that weight is set to 0, so because the rest strings are defaulted. Alright, so for walk, we're just going to say my dog pants when he walks. Alright. Oh, we're also going to include string. Okay. And sure includes string. So we're always getting in trouble without forgetting that using namespace. It's kind of a pain in the butt. Alright, so that fixes that. Anyway, so there's our implementation of our constructor, which only gets called when the object is first created. It can take parameters, so we could have another one, a constructor, which we call dog, which presets the name. Okay. Now, also, if we come back to our class definition, we can actually get rid of, we don't have to give it the parameter names. We can also do, just since they're just prototypes, we can just do this. And then define the names when we're actually building the code. But let's create a second constructor here, dog string, and so now we have to provide an implementation of it here. And what we'll do here is we will say weight equals 0 just like before, and name equals dog name. So now it presets it. And this is called a default constructor, no parameters, and this is called a parameterized constructor. So here's our walk method. All right. Now let's implement bark. Oh, wait, and we have to again put here, so it's part of class dog. park. We'll say arf, arf, arf. My name is, and then we'll use the instance variable that we have called name to output it, and then we will. Now, to be 100% safe, if you want to be really picky, you could actually just use getName to actually just get the name. That is being 100% smart if you do anything special inside your getter or setter. But anyway, let's this. Okay, for this, all we need to do is return the weight. And the reason we didn't do this is because now we could change the implementation. We could store weight as a string if we wanted to, and it wouldn't make any difference to the using code. All right, so let's say here, we'll say here weight equals new weight. And here, for example, we could check to see if the value is valid for new weight. Did I spell it wrong in .h? Oh, okay. Why is it complaining? For some reason, it's not liking that way. Let's finish up the rest of the functions and see what's going on there. Breed. Return breed. Oh, I know why. Duh. Forgot to tag it as part of class dog. If you don't, it can't see the number of variables. So set breed, make sure it's part of class dog, and we say here that breed equals new breed. Here we'll say disposition, return disposition. Here we'll say set disposition, and so forth. Okay, and last but not least, we will do name. Dog. Here we will now return the name. And now we'll do set name. Now, even though it may seem like a pain in the butt to implement all these getters and setters, it's a good idea to do so. More modern languages like C++ have easier ways to do it. But anyway, so now we've defined our dog class. And so what we're going to do, come back to our main. And here we will include dog.h. Now what we'll do is we'll create an instance of a dog. We'll say dog, my dog. Okay. That creates a new dog. And now we'll create another instance of a dog, other dog, and we'll give it the name Max. Okay. Now, I'm going to add another method to dog to make our life easier. Let's come over here to our dog.h, and we're going to implement a method called toString. And what that'll do is give us a string which we'll use to print out the contents of the dog object. So, string dog toString, and what we want it to do is print out all of the contents. So we'll say your dog is name. Okay, and then what we'll say here is it's put it on there. Its breed is /n. Oops, this is wrong. I'll put the new line here, just keep the code shorter. Its breed is breed. By the way, we didn't have a breed function there, but we probably should. Do we not have a breed number? Yeah, we do. All right. Oh. Oh, done yet. And its color is its weight is Now, if you notice, there's a couple properties we don't have getters and setters for right now. Breed and, we have breed, but we don't have a getter and setter for color. So, if we don't have one, we can't access it. So, let's quickly create one. Okay, so now we've created this. Now we're going to have to add these to our class definition. And we don't need a dot here. And white, set color, string color, string. And there we go. That should implement everything we need. Oh, you know what? I did this wrong. We don't want to print it here. We want to return a value because we'd rather have separation of concerns. We want string. So I'm sorry. So we'll say return, and we'll change this to concatenation. Obviously, I missed something in here somewhere. So here we have, the problem we have here is that weight is a double. And we haven't learned to convert yet. So we will come back to that. And so now for now we'll leave weight off for this example. So anyway, let's come back to our main. And what we'll do is we'll say my dog name equals Charlie. But we can't do that because we want to use getters and setters. So okay, and my dog dot set weight 20 pounds. And then we want to say my dog dot set this position. And we'll say here, this position is equal. And we want to say my dog dot set breed. So now, to print it out, we just want, all we need to say is my dog toString. So let's run this and see if it gives us what we expect. Dog's name Charlie. Its breed is pug. Its color is, we didn't set the color, so there isn't one. Now, we've got our other dog, which we're not going to set anything else on. And for it only has its name. Now, we could make our class more advanced by only concatenating the strings when we actually have values by using if statements. For example, we could say string. And this is an example of how we could change implementation tables. String output equals output, right? And then we'll say if name doesn't equal empty string, then we'll say output plus equals and then we'll say if color doesn't equal, then we'll do the same thing again, but this time with color. Let's read here. Okay. We'll do it again. This time we'll do it for color and then disposition. Color and then disposition. I'll say output plus equals. Equals disposition is disposition. And now we'll just return the string, so we'll get a cleaner output. So now if we run it, prints it out, and it reads a plug. But for the other one, where we don't have any of the field set, it just prints the stuff we need. So this is to show how easily you can modify something without changing its interface. All right. So, talking a little bit about object-oriented programming, a class data type describes an entire class of entities. For example, all 2D points have both an X and Y coordinate. A class for 2D points would contain data members to represent these values. Unlike a struct, access to class data members is restricted. Functions intimately related to the class have direct access to data in the class. Place functions that operate on 2D points inside the class. So, two adjustments are needed. Since the data are private by default, we need to distinguish the data from the functions. Here are the data and the functions. If the functions were restricted, nobody could do anything, so we need to make sure the functions are declared as public. Here we declare them as public. Now, functions can be accessed from outside the class while the data remain private. We can state this more explicit using the private keyword, but it's not required. Now, the second problem is the functions now have too much information coming in and going out. As we allow these functions inside the class to have direct access to the data, they will automatically have an X and Y when they execute. The functions don't need as many arguments, so we can prove our definition. So here we pass an additional point. To call a member class function, separate the variable name and the method we wish to call by a dot. When the program executes start input, it calls the input function from point 2D class with the start variable of that class. As the input function executes, it will store what the user types in start variables X and Y values. Below, we examine the code to determine the halfway point of a journey. So we have start and end. Start at midpoint, half.print, start.print again, and end.print. So here's how it lays out each class. Each instantiation has its own X and Y. Start has its own X and Y, end has its own X and Y, and half has its own X and Y. So start is initially 8.2, -4, end is -6.0 and 9.8. We call the midpoint from the start object and pass the endpoint as the object, and it computes the midpoint and stores it in the new half object. And there we go. We can define our actual implementation as this. Our implementation function just implements the various parts of the point. And we again have to put the 2D in front of there when we're implementing it. We can declare local variables within the class that we need. For example, the midpoint point, and return that midpoint. And the X and Y it uses depend on which object of the class call the method. Methods of the class have direct access to data members of the class. We can use X and Y in the point 2D method as if arguments or locals. And direct access isn't limited to the calling object. As a class method, we can directly access the data members of any object of this class. So here we can say mid.x instead of having to say mid.getx. Whenever you refer to a data member, such as item count or total price, in a member function, it denotes the data member of the object on which the member function was invoked. It is like there is a hidden parameter to the function, which there actually is, which denotes the current object, and it's called this, and we'll discuss that later. An implicit parameter is a reference to the object on which a member function is applied. When a member function is called on an object, the implicit parameter is a reference to that object. You can think of the code of a function like this: implicit parameter.itemCount++, etc. However, you don't write the implicit parameter in the function definition. The parameter is implicit. And there's a way to access that I'll show you later, or deliberately access it. Parameter variables that are explicitly mentioned in the function definition are called explicit parameters. Every member function has exactly one implicit parameter and 0 or more explicit parameters. When calling another member function on the same object, do not use the dot notation. You don't need to. When one member function calls another, you do not use the dot notation. Instead, you use the name of the other function, but they have to be in the same object. So, for example, when programmers who didn't write the class want to use the data within the class, we provide an interface using accessors and mutators. Gets would be accessors, sets would be mutators. We use mutators to protect the data. You can put error checking around it, and a mutator can check for conditions and disallow things that would violate the proper range of variables. Okay. So we've already given a demo. And here would be another example. We create a class that modifies, that is implementing a tally counter, which has operation click. And here is our class. We say we have we have one private value, reset, which resets to 0, count, and get count. So here's the implementation. It's very simple. When we hit count, it's +1. When we hit get count, it returns the value, and that's it. So a constructor is a special member function that is called automatically whenever an object is created. It is used to initialize the data member of an object. If you notice, it doesn't have a return type. It's like assembly instructions for an object, and it's a place where you can set up all the member function values as needed. The name of a constructor is identical to the name of its class. Declare constructors in the class definition. For example, class dog, and then we implement it. A constructor with no arguments is called a default constructor. It's used when you define an object and do not specify any parameters. A class can have more than one constructor taking parameters. Many class has more than one constructor. Use them to initialize the objects in different ways. So a bank account could have a constructor which takes nothing and sets a balance to 0, or one that takes an initial balance. And you set up accordingly. Joe's account uses the default constructor. Bank account Lisa's account uses the account that takes a double. Now, we've talked about this before. When you write and compile small programs, you can place it all in one file. You'll want to split your code into source files. It takes time to compile a file and waste time waiting for the compiler to translate code that doesn't change. So we don't always have to recompile. When you work with other programmers, it'd be very difficult to do it all in one file. If your program has multiple files, some of these will define data types or functions that are needed in other files. There must be a path of communication between the files, and this is done through header files. A header file contains definition of classes, constants, non-member functions, that's regular functions. The source file contains the definitions and of member functions and the definitions of non-member functions as well. So for our counter class, we'd have a header file which contains the definition, and then we have our implementation file which contains the details of how we implement it. The counter.cpp file doesn't contain a main function. Many programs could use the counter class, and each of these programs will supply its own main function and just include the counter.h file. So here we go. Use counter.h, display the counter. Here's our calorie counter. We count again, and we display the counter, which calls the get count method. To build the program, you need to compile both counter driver and counter.cpp, and like we showed before, you just say g++-o counter driver probably.exe, then list the files for it. There's another thing we'll talk about later called makefiles, which is an easier way to do all this. But a header file should include all headers that are necessary for defining the class. For example, if a class uses string, include string in the header as well. Anytime you include a header from the standard library, you might also want to include the directive using namespace standard. So that's an introduction to classes, which we will use extensively, and we will take it from there.